Hi, my name is Sarah Hankins, and today I will be giving a visual explanation on what happens when we perform finite element analysis for the one-dimensional case. In FEA, we have to define the types of elements that we want to use. Now, for a one-dimensional problem, the simplest element we can implement is a linear element, which gives us a linear approximation. Now, let's assume we are applying it to this example problem here, where the black line defines our exact solution, and now we want to implement a linear element such that we get this linear approximation to our exact solution. So what a linear element does is it has two nodes here, which are defined by node 1 and node 2, and those represent the endpoints of the element with this linear approximation across the element. Now, one thing to observe here is that our approximate solution equals our exact solution at the nodes. So at node 1, we've defined our exact solution as U1, and at node 2, we've defined our exact solution at node 2. So this observation is ultimately what's going to allow us to develop this linear approximation between our nodes. Now, to do this, we start by defining a linear polynomial approximation function, which is given as follows. And what you're going to do is we are going to utilize the observation that our approximate solution equals our exact solution at the nodes in order to develop these two equations. So now we have two equations to solve for our two unknowns, C1 and C2. And if we go ahead and do that, we get that C1 equals the following and C2 equals the following. And then finally what you do is you go ahead and substitute these C's back into our definition of our linear polynomial approximation function, and we end up with a final approximation function that looks like the following. So this approximation function, what it ultimately does is it defines this linear element or this linear approximation between our nodes. Now, if you look at the form of this approximation function, you'll notice that we have our exact solution at node 1 times a function plus our exact solution at node 2 times a function. And so these two functions have a special name. They're actually called our interpolation functions. And we are going to take the next couple of slides to really dig into what these interpolation functions mean from a visual standpoint. So the first thing we want to do is we want to single out our interpolation functions n1 and n2, and we are going to plot those individually. So the first thing that you'll notice here is that because we are trying to develop a linear approximation function, that our interpolation functions themselves are also linear. The second thing you'll notice is that our interpolation functions are these normalized functions, meaning that they're always going to fall between values of 0 and 1. Now, the reason for that is because these normalized interpolation functions, they ultimately get scaled by our exact solution at the nodes. So what does it mean to scale our interpolation functions? Well, if we take a look here at our first interpolation function n1, which gets scaled by our exact solution at node 1, what we're doing is we're taking this interpolation function and we're scaling it by u1 such that now our interpolation function equals our exact solution at node 1. We can do the same thing for our second interpolation function n2, which gets scaled by u2, and so essentially what that's doing is that's ensuring that our linear interpolation function now equals our exact solution at node 2. So the purpose of our first interpolation function is to ensure that we're matching our exact solution at node 1, and the purpose of our second interpolation function is to ensure that we're matching our exact solution at node 2. However, on their own, you'll notice that these interpolation functions are only able to match a single exact solution. That's why, if you notice up here in our definition of our linear approximation function, what we need to do is we need to add our scaled interpolation functions together. So let's go ahead and do that. If we add our interpolation functions together, where this line represents n1, this line represents n2, and then the blue line here actually represents our two interpolation functions added together. Now if we go ahead and we scale each of our interpolation functions, what you'll notice is that brings this point down so that way it matches our exact solution at U1, and it pushes this point up such that it matches our exact solution at node 2. And now we have this nice linear approximation that equals our exact solution at the two nodes, and then a linear approximation between the nodes. So it turns out that a linear function plus a linear function equals our final linear approximation. And so that's ultimately how we develop this linear approximation for our exact solution using a linear element. Now the second type of element we can implement is a little bit more complicated. It's known as a quadratic element, and what this element does is it actually gives us a quadratic approximation over our element. Now to do this, we'll look at the same example problem where the black line represents our exact solution. And now with a quadratic element, what we've done is we've introduced a third node that falls at the center of the element. So here, node 1 and node 3, those still define the endpoints of our element, but now node 2 falls at the center of our element. And so what you'll notice is that we have this additional node where we require that our approximate solution equals our exact solution at all three nodes. And by doing this, you can see we now develop this quadratic approximation between the nodes and over the element. Now to develop our quadratic approximation function, we start by defining a quadratic polynomial approximation function, which is given by the following. And again, we utilize the observation that our approximate solution must equal our exact solution at the nodes, such that we can develop three equations that allow us to solve for our three unknowns, C1, C2, and C3. So if we do the math, we end up with the following. And again, we can substitute our C's back into our definition of our quadratic approximation function. And we end up with the following function that you see here. So this function is ultimately what allows us to develop this quadratic approximation for our quadratic element. So again, you'll notice that it's in the form of our exact solution at node 1 times some function, our exact solution at node 2 times some function, and our exact solution at node 3 times some function. So again, these functions are known as our interpolation functions, and the point of them is to ensure that our approximate solution equals our exact solution at the node that it is getting scaled by. So as before, we want to go ahead and plot each of our interpolation functions for our quadratic element. And again, what you'll notice is that because we're trying to develop a quadratic approximation, all three of our interpolation functions are also quadratic. Again, you'll notice that our interpolation functions are normalized functions, again meaning that the value of them falls between 0 and 1, again because each of these three functions are ultimately going to get scaled by our exact solution at the nodes. So as before, we want to go ahead and scale our interpolation functions. So we'll start by scaling our first interpolation function by U1. And if we do that, again, this first interpolation function ensures now that we meet our exact solution at node 1. Again, we can scale our second interpolation function, and what this does is this ensures that our approximate solution equals our exact solution at node 2. And then finally, we can scale our third interpolation function. And again, if we do that, now what this is ensuring is that our approximate solution equals our exact solution at node 3. Again, on their own, each of these quadratic approximations perform really poorly, but you'll notice that here in our final function, we go ahead and we add these scaled interpolation functions together to form our final approximation function. So we want to go ahead and do that. We want to add all of our scaled interpolation functions together. Okay, so by adding all three interpolation functions, so this is our first interpolation function, this is our second interpolation function, and this is our third interpolation function. If you add them all together, you end up with a quadratic approximation function that is given by the blue line. So again, we want to scale each of our interpolation functions, and if we go ahead and do that, Again, you'll notice that our first interpolation function ensures that we match our exact solution at node 1. Our third interpolation function ensures that we match our exact solution at node 3. And our second interpolation function ensures that we match our exact solution at node 2. And so this is how we are able to form our quadratic approximation over our element for our quadratic elements. The last thing we want to do is we want to assemble our elements together to form this global solution. So for example, if this black line represents our exact solution, what we want to do is we want to implement 3 linear elements such that we get this linear approximation for each of our elements and then for our solution globally as well. So when we assemble our linear elements, you'll notice that there's this common node between element 1 and element 2, and a common node between element 2 and element 3. And so these common nodes ensure that we develop this continuous solution or approximate solution for our primary variable. So if we go ahead and we assemble our 3 linear elements, we would end up with a global linear approximation that looks like what follows. Similarly, we could implement 3 quadratic elements instead of 3 linear elements. And if we do that, you'll notice that there is still this shared node between element 1 and element 2, and a shared node between element 2 and element 3. These shared nodes are going to ensure that we develop this continuous quadratic approximation for our global solution. So if we go ahead and we assemble our 3 quadratic elements, we end up with a global approximation that looks like the following. Okay, so as a review, what we looked at today was we looked at what our interpolation functions mean for a linear element and for a quadratic element. And what we found out was that our interpolation functions are used to ensure that our approximate solution equals our exact solution at our nodes. So for example, in our linear element, our first interpolation function ensured that we reached our exact solution at node 1, and our second interpolation function ensured that we reached our exact solution at node 2. Now when we add these 2 linear interpolation functions together, we get a final linear approximation function that now matches our exact solution at both the nodes and then has this linear approximation between them. Same thing for our quadratic approximation functions. Again, each of our interpolation functions ensure that we match the exact solution at the nodes, and then we can develop this quadratic approximation over the element. So I hope this gave you a really good visual understanding of what is happening when we implement our interpolation functions and when we change our elements from linear to quadratic.